Afternoon, everyone. My name is Syed Sarup. I am an application engineer at 96 Boards, and this talks on the robotic arm control using the Qualcomm RB3. So we'll sort of be going through all of that I said right now. So what's the RB3? Why was the project made? Some design decisions, some weird ones, and what the project actually is. So what I'm not going to do is to show you guys how to make it. This is just an overview. So purpose of this project was to introduce people, developers, students to the RB3 Robotics platform and the 96 Boards ecosystem. And they show the capabilities of the RB3 board and near real-time vision processing using OpenCV. It's got a very powerful processor, so you can get up to 15 to 30 FPS depending upon how much processing you are doing there, and voice recognition, and then some motor control using an external motor control board over I2C. And yeah, so serve as an example project. So if anyone wants to start their project using RB3, you can follow the guides online, and you might be able to find a lot regarding this board and how to use this board on you just going through this project itself. Target audience, people in the field of robotics, students, and everyone else who needs something that has a bit more power than the Raspberry Pi. Yeah, it's like it has a lot more power than the Raspberry Pi. So meet the RB3. It has 8 ARM V8 cores, 4 of them running at 2.8 gigahertz. These are the more powerful ones, and 4 of them running at 1.7 gigahertz. These are less powerful ones, but still very, very capable. The GPU is a Arduino 630 and OpenGL ES 3.2. Unlike most of the boards that are out there, this in fact has a decent GPU driver, so you can play games on it. And the GPU driver is open source, so it will always be there. It has the hexagon DSP, so if you go on to the Qualcomm booth in the lobby, you can see some of the demos running on the DSP itself. It has 4 gigs of RAM, LPDDR4, and it has 64 gigs of very fast UFS storage. Expansion connectors, actually a bunch of them, so I won't read it out, but it sort of expands on the 96 boards ecosystem, and the specification. So you just have the LS1 there, and you can see smaller connectors which were added, and then you have the high-speed one and another high-speed connector which the RB3 guys just went ahead and add that. It is in a SOM-ish form factor, so you don't have to buy anything separately. It's all part of the package, but there is actually a SOM in the back, so you can take it out and add to your own board once you finish with the development. And the project overview. So the basic flow goes: I have my robot arm in front of me. I say, "Hey, July, pick up the red ball, red rectangle, whatever," and it will go ahead. It will on its OpenCV window. It sees where that actual object is. It reports it back to the servo, to the board, and then the board controls the servo. It's kind of a feedback loop till it finds it. It zeroes in on it, and it goes ahead and grabs it. So that's kind of the way to do. The other way would have been to have an external camera and then map the XYZ position on the OpenCV window, but I think this is kind of the other way to do it, is to actually have a feedback loop from the OpenCV window to make that happen. Right, so design decisions. Python, pros. Lot of examples online. You go to one website and you find tons and tons and tons of examples for OpenCV. I have rarely seen many projects that use C++ for OpenCV, although it can be done, but like everyone just seems to be using Python. And the speech recognition library is readily available, which uses the web speech API and just makes life a bit easier to do speech recognition on it. Cons, GIL or Global Interpreter Lock. What that means is you cannot run threaded applications. It will run the whole entire OpenCV stack runs on a single thread on a single core. You need to make some magic in the backend happen to not do that, but if you're writing a C program, you cannot have a properly threaded, it's time sharing is always an option, but you cannot have a properly threaded application. So in this project, what I've done is actually I run 3 or 2 separate Python scripts to actually get things running in parallel. So the OpenCV bit and the robotic control bit are two separate scripts for the same reason. But how does NumPy and OpenCV use all the cores? Because everything's written in C in the background and just used as a module. So in the background, OpenCV and NumPy are running C, C++ code, which are heavily threaded using pthreads or whatever they like. And yeah, that's how they get the performance. Right, Logitech C922 is the camera we are using for, not for its 1080p resolution, we are actually using much lower resolution. But it has pretty fast sort of autofocus, so when the arm moves, it doesn't have to, it doesn't get confused at times. And auto white balance, which is necessary if there are slight change in shade and color of the light and temperature of the light, it actually balances out pretty much immediately. So that's why I kind of went with that. The other one is OpenCV 3.2. A few of you would know that OpenCV 4 is out. It is buggy with ARM64 hardware. We have had issues with Jetson Nano and the RB3 and a few others. So the OpenCV 3.2 just compiles fine, so I'm using it. Bugs open if anyone wants to go and look at it and maybe help solve that thing. All right, project breakdown. We are getting to the good stuff. Software requirements. Wait, did I miss the hardware requirement bit? Yeah, there you go. RB3, of course, the 6th DOF robotic arm. Everything will be mentioned in the final blog I post as well as the project repository once we have sort of cleaned everything up. Yeah, so it's the board that I wrote there. It's a 6 DOF kit. It has 6 servos, and for some of the 5 DOF will work as well, but it depends which one of the servos they have taken away. So if it's like the second to last one, that's fine. If it's anyone from the base up to the third one, it's not going to work that well. So yeah, for the motor controller, we are using a PCA 9685 chip or the RB3 Robotics mezzanine, which should be announced sometime soon. But so the demo you are going to say this week is using that mezzanine, but that also has the same PCA chipset on there to control the robotic arm. So you give I2C commands to it. It like generates the PWM signals required to control the servos. Software requirements: Linaro Debian release for RB3. This runs on open source Linux kernel 5.2, which is mostly upstreamed. And you just run the install OpenCV script, which will install a bunch of Python modules, and you build your OpenCV. On the Dragonboard 410C, OpenCV takes overnight to build. On the RB3, it takes about 20 minutes. All right, so I got this question actually. How do you differentiate between the colors, and how do you make sure that they don't get confused? So this is the contours bit. What you do is we use the HSV color space to sort of assign a value or a range of the HSV color space to each color, and you need to manually go ahead, depending upon the lighting conditions, depending upon the type of object, you need to manually go ahead and move these dials till only one object is visible or the single color is visible that you want to work with. Once you have that, you then have to go ahead and manually enter that number on your code, which we'll see how it uses that. So basically then OpenCV will go, all right, so this object falls into this range of the HSV color space, so it must be that color. So for red, you will set all the values till only the red color visible, and then you'll copy the values to your code. This like helps separate different colors. That's all. Detecting the shapes. So first we start. I'm sure the code is actually pretty blurry for everyone to see, but first we start by blurring the entire frame so that all the rough edges are gone and it's easy to detect. Then we convert from the BGR color space that we are getting from the camera to HSV. Again, as I said, we are working with the HSV color space so that the colors can be differentiated. And then you perform a series of dilation and erosions to remove small blobs. So if you don't do that, the the recognition like looks blobby, it's like it will show you 10 to 15 different objects, which was a discussion earlier where someone was going to use that to detect foam. So if you just remove the dilation and erosion functions, it's actually pretty easy to detect foam formation. But in this case, we just need a nice outline around the object. And then with the contours that you just created, you get the X and Y value with OpenCV, and that's the center. So that's how the robotic arm knows where to place the object in the frame and then go in for the grab. Detect the shape. So we first use the arc length function within OpenCV to detect the parameter of the object, and then we use the approx polydp function to calculate the number of curves it has, and according to that, it can be a triangle, rectangle, or circle. Circle is usually, if you can't detect anything, you just go with circle. So I've gone up to pentagon, and then more than 5 just detected as circle, and again return the X position, Y position, so that the other script can go ahead and just start moving the arm to that location. Adding a visual overlay, this is purely a demo specific step. You don't have to do that if you're just making a robotic arm for production use, but you use the draw contours and put text functions to draw like a colored line around your object and add a text about the XYZ position. So it's nice to look at when it's on a demo table, but it's not really useful, and it will add a fair bit of latency. So you need to make sure if you're making it, if your main goal is to have it go fast, then you might not need to add this bit. And then speech recognition was very basic. I used the speech recognition library from Python, just pip install speech recognition. And so you use the default system mic, which you can change in ALSA or GNOME or whatever you're using to whatever, if any other mic you have connected, that will work. And then you use the edges for ambient noise, which works okay, but in our current demo situation, it wasn't. The noise was too overpowering. So we have a text-only mode in that as well, so you can type in your command, it will work just fine. So you listen for the source and you recognize Google Audio. So it's not using the Google Cloud Audio API, which is a bit different, which you need like a API key for and all of that stuff. This is also called the Web Speech API, which is sort of free, but not that fast and or accurate. It's still more accurate than if you did everything locally, which is like really bad. So again, not to be confused with the Google Cloud API. So that's how we do the speech recognition. There is another thing that I might have forgot to mention. I use a thing called def library in Python. What you can do is, if when you're matching the what the user had said to what you want, you can give it a list. Say, I can say color, different spellings of color, or some other word that just sounds like color, and if it finds a match anywhere around that, it will default that to color. So sometimes typo or mispronunciation, they get lost in that, and you just get a perfectly fine translation of what you said. So it's very basic and rough. I think so just as I said, I didn't add the slide, I forgot about that. So after you have gone through the diff lib, you use the close match, and you have a list of action, color, and space, and then it returns action, color, or space, which can be like pick up a blue ball, pick up a blue circle, and action could be pick up, drop, dance, whatever you want to add in there, and of course add the appropriate motion to the robotic arm. The actual motion using Python, this was done in the last 3 days, because I didn't have the proper board. I had the pre-production one. So so the Adafruit's PCA9685 library, we originally wanted to use the UPM library, but it's currently having some issue with Python, which I need to figure out once I get back, which is kind of a preferred method to do it, because that UPM library has a bunch of other drivers as well. But for the time being, we're using the Adafruit's library, which is working fine for us. So you define a min, max, and default pulse width, which is basically, you need to get all of that data from the servo manufacturer or data sheet. But I've just used a few generic ones, so the minimum is 800 and maximum is 2200, which should work for most robotic arm servos, but it might depend which one you get. And then there are just three integers, I, J, and K, which sort of track the motion of the servo, where it is, and then again for the feedback loop, you just increment them, and it will just move the servo just 1 degree forward or backward, and you can just put that in a loop. And convert degrees to PWM servo values, which is necessary because the servo function takes in actual PWM values. So we have the pulse width function there that does the whole conversion. And if you see the map function just on top of that, that's the one I've taken from Arduino earlier, and that works just fine like that. So yeah, so that's the main motion part. I think there's one more for motion. No, it's actually not. So the other thing we just do is we put the PWM.setPWM stuff in a few while loops. So the first one goes and make sure that the arm is at the X position, and the other one is make sure that it's at the center of the Y position. So that's the object is then centered on the OpenCV frame, and then you can just move two of the servos at the same time to make sure that it more or less goes perpendicular to the ground instead of moving forward when the arm is going down. So you center it, and then you move it down, and then it grabs it. So while the arm is actually doing the motion of moving up and down, you don't need OpenCV. So bringing it all together, again, due to Python GIL, what we are doing is we are using two different scripts, and we are sharing the data using something called memcached, which opens up kind of a TCP/IP-ish local server within the board, and then you can just pass values through that to different scripts. And just use the PyMemcached library for that. It can only store string values, which is a bummer, because I want to transfer lists, so that it now has to be converted into JSON. Then JSON gets converted to string, goes back to the other script where the entire opposite step happens, where JSON is then converted back to lists so that I can use it. Shape.py, this is the shape recognition thing. Again, I just explained how that works. You get the X and Y data, you get the shape data, which has the X and Y data, the contour, and the color of the object, and that just gets passed again through the JSON stuff, and then memcached to the other main.py, which gets that data, extracts the X and Y position, and then moves the arm to the X and Y position object till the object is on the center of the OpenCV window, and then it starts slowing the arm until it reaches a predetermined height, and then it grabs it. So the other option you were thinking is to add ultrasonic sensor, distance sensor on there, but that didn't work out because the arm was already kind of getting heavy with the camera. So we just hard-coded the height it has to go till, and then perform a simple pick-and-place operation. All right, so that's sort of at the end. Thank you so much to Lauren. He is at the Qualcomm booth. I'm not sure. I don't think he's sitting here. He's at the Qualcomm booth. He was the one from Qualcomm Robotics for creating the 96 boards RB3 platform, as well as sponsoring this project. The Qualcomm landing team, of course, for all the support, and the enablement of the Debian builds with this board and mainlining of the kernel. They've done a really awesome job. So it only took us 6 months to get the board and another 6 months to have a full Debian build running with Linux 5.2. It's pretty amazing. And then Don Harbin, who actually did the OpenCV M&M demo on the 820C a few years back. And the contouring dial thing that I showed in one of the previous slides is actually just taken from one of his demos, which is pretty helpful because I didn't have to figure that stuff out. And PyMate search, as I said, there's a lot of stuff available about OpenCV on Python, and that's one of the biggest sort of collection there. Right, so I think that's about it. Resources, yeah. It's a work in progress library, so the code might not be very readable at the moment. Servando had some troubles and was screaming at me. But yeah, the blog series is well on its way. We are 2 blogs away from the final blog. And the documentation for the RB3, if you want to get one and work with it, is all on that link. And you can reach to me on my email address or IRC or join our 96 Boards Discord. The links there, you can either use it or like I can give it to you personally. Again, and thank you so much. So if you guys have questions. No? All right. Yeah.
Oh no, a lot of pressure. Hello? Okay, cool. That's a lot of pressure. Well, I'm a pretty big newbie in Python, and so by no means, I probably don't know what I'm talking about, but I recently did a project where I was trying to do like threading, but then I kind of found myself Googling stuff and ended up on multiprocessing. I was wondering, was that at all a possibility for you?
So there are, I think, two different libraries. One's called Python multiprocessing, one's called Python multithreading. Both of them, I'm not entirely sure how different they are, but both of them are doing like time sharing based stuff, because Python from the ground up has this issue of GIL lock. Like it cannot do proper like POSIX thread multi-threading that you can do on C. So that's always been an issue. I'm not sure what's the actual difference between the two.
Okay, thank you.
All right then. Thank you so much.